All right. So last lecture we actually introduced just a bunch of forces, and it was more of a conceptual discussion than it was like doing practice problems or anything like that. So this lecture we're actually going to follow up, do a couple practice problems. We're not going to do sort of every possible case of forces interacting on objects. We're just going to look at a few, and these are going to involve essentially mass, weight, and gravity. So let's think about Newton's first law. So with Newton's first law, this is the whole idea that an object at rest stays in rest, an object in motion stays in motion, unless acted on by an outside force kind of thing. And that's sort of stated here. So an object where the net forces, remember, there could be 20 forces acting on something, but if they all add up such they cancel each other out, that object, when those forces do that, is in equilibrium. So this could happen to an object when the object is at rest. So maybe friction is keeping it from moving, or it's just got gravity down, the normal force up, and those are canceling out in the y direction. So when an object is at rest and it's staying at rest, we call that static equilibrium. And for those of you that are wanting to go into civil engineering, this would be engineering statics. Basically, that's the study of when all the forces equal zero. So like you want all the forces on your bridge that you designed to equal zero. But when an object is moving in like a straight line with constant velocity, as long as the forces are balanced, it will do that forever and ever. Okay, so this is actually kinematic equilibrium, and this is part of dynamics, where the thing you're studying is actually moving, but just for this one instance, for whatever reason, the forces are balanced. So the key here is to remember that with Newton's first law, the motion will always be straight line motion because there's no accelerations, no forces to change that from the line that this object is traveling on. And there's also no forces that will actually increase or decrease the velocity. In both of these situations, since the net force equals zero and there's no acceleration, you know that you can break up the x components, sum those up, and those have to equal zero. And you can also break up the y components because you know those also have to equal zero. When we think about these equilibrium problems, it's going to work the same way, or at least in a very similar way, as the previous problems did that we worked on. So the 2D kinematics problems. So essentially, you want to model the situation. And this is, of course, just making the simplified assumptions. And you want to use the particle model. You want to visualize. Okay, so we need to set up a coordinate system. Okay, and this is going to be true for pretty much all of these kinematics problems. You want to define the symbols, so we'll have like gravity, we'll have mass, you might have a distance, delta x, something like that. We want to identify all the forces using a free body diagram. And with the free body diagram, that's just essentially placing the particle at the origin, and then making sure, I can do a vector, or at least some vectors in different color, making sure we have all of the forces acting on this particle, make sure we have those included. Okay, and we want to identify the unknown, so maybe we're solving for some mystery force. So we could say maybe force, I don't know, force 3 in the problem. What is it? So once we set this up, we should be good to go. The physics happens here. The rest, when we actually do the algebra to solve this, when we sum these forces up, set them equal to zero, because it is an equilibrium problem, that's just algebra from there on. And then, of course, you want to check your units, and you want to check to make sure the magnitude of your answer actually makes sense. So let's look at this one quick example here. So you and two friends find 3 ropes tied together with a single knot and decide to have a 3-way tug of war. Avery pulls to the west. Okay, Avery's pulling to the west, while Brandon pulls to the south with 200. Oh, no, let's see. Adrian pulls to the west. Sorry, Avery pulls to the west with 100 newtons, while Brandon pulls to the south with 200 newtons. How hard and in which direction should you pull to keep the knot from moving? So essentially, we want to keep the knot over the origin on this free body diagram. Okay, so we need to know the magnitude, how hard, and in which direction. So we also want to know the angle theta. All right, well, we read the problem. Next, we need to model. Okay, so we've got a picture here. Everything checks out. We've got Avery pulling to the left or the west with 100 newtons. We got Brandon pulling down with 200. And then you pulling up to the northeast, I guess, to cancel out these 2 other pulls. Okay, so we've drawn a picture. Next would be to do to construct a free body diagram and label all those vectors. Okay, so remember there's no net force. So it's important to remember that when we sum up these 3 vectors, we could even do the tip to tail method if we wanted to, but when we sum them up, the third tension, T3, your tension, you need the components of it to make sure they cancel out everything else. Okay, so these forces, when you sum them up, should equal 0. All right, so you'll notice we've also established a coordinate system. We need that so we can actually draw vectors. And we've named and labeled axes and everything, all of the variables we don't know, all the variables we do know, we've got those named. And the last thing is we've written out our knowns, and then we finally identified the things we want to figure out. We've identified our unknowns. All right, so it looks like everything's in place. So now let's talk about how we can actually solve this. All right, so thinking about the free body diagram, we know that these forces, when we add them up, okay, we can do that in second law. We know this has to equal 0 newtons. That's going to be in the x direction and the y direction. Okay, so here in the x direction, we have the x components of those 3 tensions. Okay, that makes sense. So we're going from the full vector equation down here to just the components. Okay, well, in the y direction, same thing. We have the y pieces of tension 1, tension 2, and tension 3. We don't know what they are, but we can list them out and sum them up. We know they have to equal 0. Now in the x direction, we have, okay, let's go through these. So I'll use a different color. I'll use orange for the x direction. Okay, so we have negative T1. Well, that makes sense because T1 is indeed pointing in the negative x direction. Okay. Well, what's the x component of the second tension? Well, you'll notice that the second tension just points down, so there's no x component. So for this one, there's no x. Okay, so we can just ignore that. Now for the third tension, this one is pointing in 2 directions. It's got some piece in the x direction and it's got some piece in the y direction. Okay, so we only want the piece in the x direction right here. Now we can actually get that from just taking the cosine of the angle. So we have the magnitude, right? We don't know what the magnitude is. We need to figure it out, but we sure can write it symbolically. So we have the magnitude times cosine is going to give me that x component that we're after. Now let's think about the y direction. Let's do green. So in the y direction, okay, well, the first tension, you can see is lying on the x-axis, so there's absolutely no y component at all, so we know it's going to be 0. Now the second tension, you'll notice this is good because here all of that second tension is in the y direction and it's negative. Okay, so our tension is going to be negative, or our y component of T2 is just the negative magnitude. We already know the magnitude because it tells us, so we can plug that in later. Now, here's where it does get a little tricky. We want the y component only of the third tension. Okay? Now, since we can write out the trig version of this, essentially, how can we write out this y component in terms of the hypotenuse? We know that we can take the sine of this angle, and that's going to give us just the y component of this full vector. Okay, so we're just going to take the y component of T3. We don't know what T3 is, again, but we can write it out. Okay, so we take that y component, that gives us our y direction of T3. Now the whole idea here is we can just sum the forces, right? So we want to just add up everything in the x direction and y direction. Okay, let me get rid of this. All right, so I've done that here for the x direction first. Okay, you'll see that I have included all three pieces, T1, T2, T3, but again, T2 is 0. So that goes away, that's just 0. Now we just have the x component of T1 added to the x component of T3. We know this has to equal 0. Now, if we just do some simple rearranging, essentially just move T1 to the other side, we see that the amount of tension T1, so all of that tension from Avery pulling in the negative x direction, that has to be canceled out by just your x component. So just the x component of T3. Okay, same thing over here in the y direction. Let's see what goes away here. Looks like T1 goes away, so we know that's 0. All we're left with is just all that negative piece from, who was it? Brandon, I think. All that negative piece from Brandon pulling down toward the south direction on T2. That has to be, you have to cancel all of his pull, all of his tension out just by your y component of your vector. Okay, so we have all of his strength pulling down. You got to cancel it out with just one of your components. The other component is dealing with Avery. So you know that these have to equal 0 since they're canceling out. And then again, a quick rearranging shows exactly kind of what we come up with intuitively. Your y component has to cancel out all of this pull. All right. Now let's actually do the last little bit, put all this together. Okay, I'm going to see if I can zoom in here. So let's figure out what this angle needs to be for this to actually work out. Okay, so we know that essentially using tan of theta equals opposite over adjacent. Okay, so we know that tan of theta is opposite over adjacent. If we take inverse tangent on both sides, we can solve for theta. Now our opposite, we don't know, we don't have a number for that magnitude, but we do know that it's just the y component of your tension, the tension you're supplying. Okay, and we've even labeled it here. Okay, so we know this is, we don't know what it is, we can write it symbolically, so that's good enough for now. Now, the other piece here, the adjacent piece, well, we know the adjacent piece on this angle is just going to be your x component. Okay, so we know we're after this piece. Again, we don't know its magnitude, but we can write it out. Just the cosine of the tension you're pulling with. Now, we can go back to our two equations that we come up with in the x direction and the y direction, and we know that the y component, well, that has to equal to T2, so we can just make a quick substitution. The x component, we know that has to equal T1, again, quick substitution. All right, now remember, these values were given to us. So we know that T1 by Avery was 100 newtons. Okay, so that's just from the problem. And we know that T2 by Brandon was 200 newtons. So we can actually, now that we've made this intermediate substitution to T2, T1, we can actually plug in the values from the problem because we know them. Okay, and then we can just do an inverse tangent and get our final answer. So we still don't know how hard you need to tug on this rope, but we do know it needs to be at an angle of 63.4 degrees. All right, now to actually figure out that second part. So what would the magnitude be? So essentially all we need to do here is just take one of these equations from earlier. So we have what? T1 equals T3 cosine theta. Well, all we need to do is just rearrange it. We can divide both sides by cosine theta, okay? And that's going to give us this equation right here. Well, we know what T1 is, and we know what angle we're pulling at now, so this just becomes a simple plug and chug, and it turns out you'll need to pull with approximately 224 newtons at an angle of 63.4 degrees. Okay, so this was an example of everything being static, not moving, all the forces equal 0. So let's think about another example where we have something that's moving, but there's still static equilibrium going on. Okay, so we got a car with a weight of 15 kilonewtons. It's being towed up a slope of 20 degrees at a constant velocity. Friction is negligible. Okay, so we won't worry about friction right now. And the tow rope that is being pulled with is rated at 6 kilonewtons. Okay, so anything over that, it will break the tow rope. So essentially, we just need to calculate tension. How much tension is actually there, and we can compare that to this number here in the problem. So really, the question is, will it break? Okay, well, let's model the situation. So we've got a picture, we've drawn a coordinate system, we've added our vectors, we've added our knowns, and we've identified what we want to find. So we want to find the tension here. You'll notice a cool trick, and this is important. What you can do is you can actually rotate your coordinate system at any angle you'd like. So the idea is you want to rotate your coordinate system so that you have the most vectors lining up with your axes. See here how we have the normal force and we have tension right along the x and y axis. If you can rotate a coordinate system to do that, it makes the algebra much easier. You can do it at any angle you'd like, but this just makes things simpler because there's less trig functions floating around. Okay, so on this car, we have the normal force from the ramp, which makes sense. We have gravity acting down on it, and then we also have the tension from the rope. So there's no friction, there's nothing resisting that motion. Okay. Now here's our free body diagram. So let's sum these forces. So we know there's only 3 acting on it: tension, normal force, and gravity. Now we can break this up. We know all this stuff's going to equal 0. Okay, so when we actually start breaking up our x and y components here, we take all the x pieces of these vectors, all the y pieces. These also have to equal 0 newtons. All right, so in the x direction, let's think about what we have. We have, well, the x component of tension, you'll notice that tension is actually, let's see, there we go. So all of tension, since we rotated our coordinate system, it's all in the x direction. So this is just a full-on value of t. We're good to go. Well, in the x direction, there's also no normal force, so this checks out. That makes sense. Now, you'll notice that there's a little bit right here. There's a little bit of gravity there's a little component of gravity trying to pull us back down or trying to pull the car back down the ramp. So we need to account for that little X piece. Okay, so there's a small component of gravity. Okay, so there's just that little piece pointing down the ramp. We need to account for it, and we do that here. So we just find that, notice it's the piece opposite the angle, okay? So we need to use essentially just the sine so we can get that piece. Now, in the y direction, same process. We know that there's no tension in the y direction because the tension is running along the ramp. Well, in the y direction, we know all of our normal force is going to be pointing up because that's what the normal force does. It's always perpendicular. And then there's going to be, let's switch colors. Okay, so we have our normal force in orange here pointing up, but then there's also this component of gravity. So this is where the much larger piece of gravity is pointing down. Okay, so we need that y component of gravity. Because of the angle we're looking at, this y component, the orange here, that's going to be adjacent to the angle, so we need to use cosine. Now, when we sum up these forces, we have some stuff going on here in the x direction and the y direction, but we just sum these forces, set them equal to 0. Okay, hopefully you see where these two equations came from. And from this, we can get all the information we need about this system. Okay, so we're just looking for the tension in the rope. I want to check something really quick. Just give me 1 second. Yeah, okay. Excellent. So we're looking for the tension in the rope. Well, we can solve for tension right here in this first equation. All right, so the tension would just have to equal the the x component of the friction. Okay, so we know it's 15 kilonewtons. We can plug that in. We know the angle is 20. That was given to us. Okay, and it turns out the tension in this rope is just 5.1 kilonewtons. Now, since the rope is rated for 6 kilonewtons, we're good. The rope shouldn't break. All right, so there was 2 examples of essentially Newton's first law, where we have something not moving and the forces equal 0. We also have something moving because the car's being towed at a constant velocity. In both cases, Newton's first law applies because there's no acceleration, all the forces are balanced. Now, before we start talking about Newton's second law, where there's forces acting on us or acting on objects, let's actually define some of these forces and talk about those. So we'll start with mass, weight, and gravity. So mass is just an intrinsic property of an object. That's just how much of that object is there, okay? So I like to think of mass as essentially how much of an object is there. Okay, so objects have mass. Now let's talk about gravity. So gravity is an attractive long-range force between 2 objects. You remember the discussion of contact and long-range forces. And gravity is a force that acts on mass. So that means if 2 particles have mass, there's going to be a gravitational interaction between them. Now, it turns out Newton's law of gravity says that when you have one object 1, okay, and it's got mass, it's going to be pulling on object 2. So the force on object 2 from object 1, so the force of 1 on 2, at least the magnitude of the force, is going to be the same as the force of the second object back on the first one. Okay, So we have, if you look over here, before we talk about this, the rest of this equation, if you look at the picture, we have some distance between two massive objects. So mass 1, mass 2. Okay, so they're going to want to go together because they both have mass. They both have this gravitational attraction. So the force that's pulling mass 1 has to equal the force that's pulling mass 2. Okay, so this is Newton's third law. Um, so Newton's third law is the whole equal opposite reactions. We'll talk about that more later, but just know that these two forces have to equal each other. Now, because this is a long-range force, the further away these objects are, the weaker the force is going to be. Okay, so R here is the distance between the centers of the objects. Okay, and you'll notice here in the equation, it takes in Newton's gravitational constant G, which we'll talk about later. Okay, and then you also include the mass of both objects. So that makes sense. Now, what happens is when we divide by r squared, that's going to cut this force, right? So the further away, a really big r value in your denominator, that's going to mean weak gravity. But if they're close together, so if r is really small and you have a small number in your denominator, the gravitational force is really strong. So if we were to draw this out in a plot, we say, okay, we're going to plot our distance r between the objects, and we're going to plot the force that these two objects feel, the gravitational force. Okay, so we'll say Fg. What you're going to see is essentially this drop off. So as r gets big, or the distance between them gets big, the force, the outcome force gets really small. So this is called essentially just a 1 over square law. And this you actually see a lot in nature where forces drop off with a 1 over r squared proportionality. And that's what this little symbol here means. It's like an open infinity. That just means it's a proportionality constant. So what's happening here is these objects, as they move away, because it's a 1 over square law, a proportionality constant, your force between these two objects is going to decrease. So let's think about how we can apply Newton's law of gravity on Earth. Okay, so let's consider this object, let's consider this object M. I guess it's just a ball, maybe in free fall. Okay, and it's a little bit above the center of the Earth. So it's some height h here, some height h above the center of the Earth. Okay, so we have the mass of the Earth, which is big M. We have the mass of the object, which is little m. Okay, and we have the radius of the Earth. And there's also Newton's gravitational constant, which is just a number. You can think of it as a scaling factor. Okay, we can put all these pieces together and actually calculate the force due to gravity, okay, on this object. So this is going to be our force due to gravity. Now let's plug this in. So we have big M, little m for the mass of the Earth, mass of the object. So it's distance away. So what's weird here, you might think, is I just plugged in big R, the radius of the Earth. So now the question is, well, what about the height? Okay, so what's going on here is I'm saying, well, the radius of the Earth is so big, and h, the height, the altitude of this object above the radius of the Earth, or above the surface of the Earth, is so small, I'm saying that h is really small. Okay, so we can ignore it. So we're just going to consider the distance from the center of the Earth, which is just r. So this is just an approximation. All right, now, okay, we said that there. We're going to ignore h. It's going to be really small. Let's use Newton's second law and free fall. Okay, so Newton's second law says we can sum up the forces, and that's going to tell us our acceleration. Okay, well, the force due to gravity We get that from here, right? We just plug that in. That's the only force acting. Well, now look at what happens. Essentially, we have, okay, we know that this thing's going to fall at negative g. Okay, so here's our acceleration. And we know it's going to be negative mass times g. Well, over here, the equation I just brought down is also negative mass times all this crap. Okay, so does that mean to make these two things equal, g has to equal all this stuff inside. That's going to make the left-hand side and the right-hand side of my equation equal. Okay, so it turns out the gravity of the planet Earth, or the gravitational field, is actually g times the mass of the Earth divided by r squared. And this will work for any planet if you know the mass. Okay, and then we also have the force due to gravity, which is just mg down. So just a little more on gravity. So when an object is in free fall, Newton's second law predicts that the acceleration of the object is going to be negative g. So that checks out. The acceleration we've been using works out for us. So all we do is think about the object in free fall. Okay, so the only force acting on it is gravity down. Okay, we just showed that that's going to be negative mg, or mg in the negative direction, because that's the force due to gravity. Well, these masses cancel out, and we're just left with negative g. So Newton's second law checks out. Generally, g is called the gravitational field of a planet, and its value is essentially influenced by the mass of the mass and size of the planet, because it's how much of the planet's there, and then of course the radius of the planet. All objects on the same planet will have the same free fall acceleration regardless of the mass, I should say, of the objects. Okay, so that's why we have this nice uniform gravitational field. Everything falls with an acceleration here of negative 9.8. And of course, you can calculate the gravitational field for other planets if you need to. All right, so with this idea of mass and gravity acting on it, we could talk about weight. So with weight, you need to know that it's not the same thing as mass. So this is super important. Mass and weight are very different things. So mass is that intrinsic property of an object that's always the same no matter where you're at. You could put something on the moon, it has the same mass, but the weight depends on the strength of gravity. Okay, and the situation in which it's measured. So there could be some situational things that will actually cause your weight to increase or decrease depending. So you can kind of think about measuring weight as like a spring scale. So anytime you step on a scale, you can see down here in this bottom picture, anytime you step on the scale, essentially your weight or your force due to gravity is pushing down, and then a spring in the scale is pushing back up. Okay, so the idea is that the amount of compression by the spring, okay, is wanting to push back up, but that amount of compression or that amount of deflection is going to tell you what the weight of an object is. Okay, so essentially just by sensing compression, that's how the spring can tell you the weight of an object. Yeah, so the key takeaway here is, in this case, the force due to gravity is acting downward and the spring is acting upward. And then that deflection will let you calculate your weight. So if you think about a quick free body diagram, add up the forces, you have the spring force up, and you have gravity down. Well, you're not moving up and down, so these have to equal 0. Okay, so it turns out your weight, or the weight of any object, is simply just equal to that spring force. So your weight, we can even call it a vector, is just that force due to gravity. So the idea here is force from gravity is your weight. There we go. Okay. Let's do just one quick example here. So an astronaut, this astronaut weighs 800 newtons while standing on Earth. So if he weighs 800 newtons while standing on Earth, what is his weight on Mars? Okay, so the gravity on Mars is, or the acceleration due to gravity is 3.76 meters per second squared. Okay, so we know what his weight is, it's 800 newtons, but we need to find out his mass. Okay, how much of the astronaut is there? How much are we going to take with us when we go to Mars? Okay, so that amount of astronaut we're taking will be the same on any planet. All right, so we can actually just use the weight equation more or less. So we know that Fg, and this is on Earth, mg. Okay, so we're going to just solve for mass, okay, and then plug in what we know. So we know he's 800 newtons divided by gravity here on Earth. That's going to give us his weight of about 82 kilograms. Okay, now we can just use the same equation again and calculate his weight on Mars. So this is just F equals mg, okay? But notice we're going to use his mass as calculated from Earth multiplied by his acceleration that he would feel on Mars. And it turns out his weight's going to be 307 newtons. So it's cut by over half if he goes to Mars. All right, so just a quick summary. We've talked about static equilibrium, so there's no motion. Okay, the forces equal 0. So dynamic equilibrium, there is uniform motion. But the forces, when you sum them up, still equal 0. It's important to remember that weight and mass are not the same thing. And Newton's law of gravity, which we'll probably use later, is just the multiplication of the masses times the scaling factor, g, and then you're going to cut that. So we're going to cut it by the distance between objects. Okay, so that's everything you need to know for essentially weight, mass, and gravity. So we'll continue to build on this in the next lecture. We have other forces that we can introduce, like friction, and we'll start building up lots of scenarios where we can actually analyze through the lens of forces a lot of motion and the characteristics of these systems and interacting particles.